Historically, one of the two big problems in calculus involves finding instantaneous rates of change of functions. The concept that solves this problem is called the derivative. And one way to conceive the derivative is to think of a curve's slope at any given point. Slope, of course, is a number assigned to a line, a straight curve, to describe the line's steepness. And the slope of a line is a constant, and therefore thinking of a line slope is a very natural thing to think of. Thinking of a curved slope is not so natural. It's a different thing altogether. But we're going to try to do that. We're going to consider a function that describes the surface of a mountain, and we're going to try to imagine poor Sisyphus, I hope I'm pronouncing his name correctly, Sisyphus pushing his boulder up the mountain. Sisyphus is the devious character in Greek mythology, condemned to push a boulder up a mountain for eternity. He committed some audacious crime, and the gods condemned him to push this boulder up the mountain, and we see him there. Okay. Alright, we have a clear picture of Sisyphus here, pushing his boulder. And we're going to suppose that he starts his task at the base of the mountain with coordinates 0, 0. So here's the coordinates 0, 0. There's our y-axis. There's our x-axis. And we're going to think of this curve y equals f of x. So the mountain side there is y equals f of x, and the function gives the height of the mountain above any point x. And our hero is captivated with the steepness of the mountain at any given point. At some points it's really difficult for him to push that boulder up, and at other points he can rest relatively easier. If he comes to a kind of a shallow or flat place on the mountainside, rolling it will be a lot easier than at some cliff face. Okay? Now the derivative of f of x we denote with f prime of x, and f prime of x can be thought of as a function that gives the slope of a curve. Does that help? The derivative can be thought of as a function that gives the steepness or the slope of a curve at any given point. So it gives a rise over run ratio, if we use our terminology from the steepness of a line, for the curve. Okay? For instance, let's suppose that after a units in the x direction from the base of the mountain, our hero is at a point on the mountain where he only has to force the boulder up a little in order to gain a lot of distance over the horizontal ground. Like, let's say we're right here. This is point A. So that's point A, comma, f of A. And when he gets to that point, we can see if we superimpose a line, let's see if I can find a ruler, we can see that it's really not that steep. The curve at this point is just not that steep. Is that showing up? Okay. So to go 1 unit in the horizontal direction, let's say this is a plus 1 here. So that in order to go over 1 unit in the horizontal direction, he only has to rise this tiny little bit right there. So that the derivative of the function at a is equal to the rise of the run. Well, let's say that rise amount is just a small amount, like 1/4, but his run was 1 unit forward, so we have 1/4 over 1, so we get 1/4 or 0.25. Now let's compare that to another place on the curve. Like say, let's take point B here when you first started over here, and then let's try to go over one, let's cover the same amount of ground, just 1 unit along the ground. Can we still see it? So let's see how steep the curve is at that point. If we superimpose a line here momentarily just to kind of help us see it, we see that in order to cover 1 unit along the ground, he's got to go quite a bit. He's got to go up 1 unit as well. So we see that the value of the derivative at b is a large number. Let's say that's 1, and he went over 1 unit, and so the value is 1. So we see that the derivative has a large value where the curve is quite steep, and the derivative will have a small value where the curve is flat. And we can imagine that if Sisyphus were to continue to push his boulder, let's say this is our mountainside, and then there's the peak, there would come a point where he would be able to rest for a moment before the boulder started moving down the other side of the mountain. And at this point, the derivative, let's call that P for peak, at point P, we see that the derivative he wouldn't have to push up any at all. So we might have a steepness that's 0. And then our steepness might start as the mountain, he starts to descend the mountain. We might think of the derivative in negative terms because he would be going down for every unit over that he goes. So at this point here, in order to go over a unit, he would go down and over, so we'd have a negative divided by a positive, and so the derivative at that point would be negative. So this metaphor of Sisyphus pushing the boulder up the mountain is one way to help us visualize the derivative.